We've got a multimeter plugged into this outlet here. It's reading about 123 volts. When I plug this light bulb in to the socket, it works fine. And we're still reading about 123 volts. And here we have another outlet. It also reads about 123 volts. However, when I plug this light into this socket, it goes from 123 volts down to about 2 volts. And the light bulb doesn't work. What's going on here? And how is this possible? In this video, you'll learn why this happens, how voltage sources work, why they have limitations, how loose connections can compromise them, and how you can use the LoZ function to reveal such problems. What we actually have here is a compromised voltage source, a situation that is quite common and often necessitates the use of a LoZ meter to detect. But what exactly is a compromised voltage source? It is one that cannot deliver the amount of current it was designed to. All voltage sources have internal resistance, also known as their output resistance. Although the term impedance is normally used with AC current, let's keep it simple. The internal or output resistance of a voltage source like a 120 volt AC outlet is very, very low, typically less than 0.5 ohms. This low output resistance allows it to supply a substantial amount of current without a significant voltage drop. For example, if you were to try and draw 10 amps from the source, it would only result in a 5 volt drop across that 0.5 ohms of impedance. So we've got a form of a kilowatt meter here. I'm going to test the current draw of this hair dryer. We're going to use that current draw to determine how much voltage drop should occur at this outlet. So I'm going to turn this hair dryer on. So we've got about a 12 or so amp draw in this hair dryer. So now I've got it plugged into this outlet here. And so based on our current draw reading of around 12 amps, we should get more than probably 1 to 5 volt drop when we turn it on. So it dropped a couple of volts there. That falls in line with what we expect our output impedance of this outlet to be. On the other extreme, a typical 9 volt battery has an internal resistance of about 5 ohms. Consequently, attempting to draw just an amp from it would drastically reduce its voltage, as that current times the internal resistance would equate to a voltage loss of about 5 volts. This is a 9 volt battery, which is a relatively weak voltage source as compared to a 120 volt outlet. It's measuring a little over 9 volts. And what I want to try to do is draw 1 amp of current off of this. Ideally, I'd want about a 9 ohm resistor, but I don't have one, so I've got a 10 ohm resistor. That's pretty close. I'm going to draw, using this, approximately an amp of current. And given that the 9 volt battery has about on average, 3 to 5 ohm output resistance, this should drop down maybe 5 volts, somewhere between 3 to 5 volts when I put this resistor across here. Note that this is a 7 watt resistor, because if you were to have 1 amp of current flowing through a 10 ohm resistor, it's going to dissipate 10 watts. So this is a 7 watt resistor. It's going to easily be able to handle it for a couple of seconds. What you don't want to do is use a small resistor like this, because you will burn yourself if you do that. And again, don't try this at home. So I'm going to go ahead and measure this voltage here. And it drops down to about 5.5 volts. So it did drop down significantly, and that indicates approximately about a 5 ohm output resistance of this 9 volt battery. However, what occurs when you have a solid voltage source, such as a 120 volt outlet, that has a loose connection where the wire attaches behind it? What if this loose connection has a resistance of a few thousand ohms? This can be called a compromised voltage source, because any attempt to draw current from it will result in a voltage drop across that loose connection. If you were to test this outlet with a regular voltmeter, it would display a reading of 120 volts. So here I have this outlet connected to 120 volts through a couple thousand ohm resistor, which represents the loose connection to the outlet. This is a light bulb socket that is plugged into the outlet. The light bulb is currently unscrewed right now for this demonstration. I'm going to go ahead and turn the voltage on. And notice that even though we have a few thousand ohm resistance here in this loose connection, the meter is reading 120 volts. So if you were to go test this outlet with a regular voltmeter, because this is on traditional volt reading mode with a very high input resistance, you're going to read 120 volts and you're not going to know any better. You're not going to have any idea that this outlet is bad. What happens if I screw this light bulb in? We're still reading in traditional volt reading mode. If I screw this light bulb in, look what happens to the voltage at the outlet. Voltage has dropped down to 2 volts. You see the problem here. What if this was an appliance? You plugged it into the outlet and you assumed that the appliance was faulty and you replaced the appliance. You plug the new appliance in into the same outlet and you have the same problem. So it wasn't the appliance or the light bulb that was the problem, it was the outlet all along. But you're reading it with a regular voltmeter, it reads 120 volts. So what can you do? Well, if you have a LoZ meter, I'm going to go ahead and turn this voltage off here. I'm going to put on LoZ mode. Now if I want to test this outlet, I'm only reading 71 volts. A regular 120 volt outlet should have no problem supplying 120 volts to a LoZ meter, and the LoZ meter should not affect it, not even perceptibly at all. So by using a LoZ meter with this outlet that has an upstream loose connection of a couple thousand ohms, we're reading 75 volts because this was putting a load on the circuit. And the voltage is being split, the 120 volts being split between this resistance here and the internal resistance of this meter. So this tells us we have a bad outlet. So the solution here would be to repair the loose connection, and so that you have a solid voltage source again, and then you'll be back in business. So a little about LoZ theory. Whenever you read something with your meter, you create a series circuit, or two loads, where the original voltage source is roughly split up among the two loads. The highest resistance gets the most voltage, whereas the remaining resistance gets the difference. So when measuring compromised voltage sources, your meter, having a greater than a 5 million ohm input resistance, may still read most or all of the original voltage source, making you think that what you have is a solid voltage. However, LoZ brings things into light. The low input resistance, typically around 3,000 ohms, of the LoZ mode, puts a load on the circuit, letting you know that you have a problem. For a full explanation about LoZ theory, click the link down below in the description of this video. And to purchase a quality LoZ meter like this one, there is also a link in the description of this video. In this video, we learned the difference between a strong and a weak voltage source, and that the internal or output resistance, or impedance, is what determines the strength of that source. We also learned what a compromised voltage source is, and that upstream loose connections are one of the most common reasons for them. Upstream loose connections come in many forms, like this dryer terminal block, this motor relay on a circuit board, and this compromised dryer cord, all of which prevent a load from receiving the amount of voltage needed when drawing its specified amount of current, yet may read a full voltage when measured with a traditional voltmeter. We also learned how we can use the LoZ meter to detect such upstream faults where a traditional voltage reading mode is unable to detect them. Thanks for watching. See you in the next video.